So I'll wait for a few more minutes, give somebody else a chance. So guys, can you see my screen? Hello. Hello. So is my screen visible? Okay, nice. So what we'll do today is start with some discussions about the last week's assignment, and then we'll draw out some problems out of the current week's content which has been taught to you. So for that, let me share you the assignment from our last week. Okay. So yeah, so this is our last week's assignment, and first question says that you have to determine the kind of metal forming process and the corresponding product we are getting out of that. Okay, so the first one is there are two processes given in the options where forging and drawing. Now, forging, is used for metal compression, compression of a slab. So, forging goes with slab and drawing goes with wares. Okay, so option B can be a right option here. And then you have metal forming is caused by, of course, this has been discussed elaboratively in our last class. So here you can see that plastic deformation is the primary reason of deformation of a product during metal forming. And of course, there are different regions of deformation where plastic deformation takes place, primary regions and secondary regions. All those have been discussed earlier. So you can break that, of course. And then the third question said average flow stress. That's a simple formula. So this was extensively discussed, and problems are also solved out of this topic. So average flow stress, goes to flow stress corresponding to a strain, and being divided by the strain hardening exponent n to an addition of 1. Okay, so sigma by 1%, that was actually taught to you. And then the fourth option says which of the following processes is not a type of bulk deformation process. So bulk deformation takes place in case of metal forming processes such as drawing, then forging, okay, then any type of extrusion, and then shearing is actually a cutting process, okay, of sheets, sheet shearing. So shearing is not a bulk deformation process. Then the fifth question asked if the strength coefficient is 680 megapascal, so strain hardening exponent given as 0.25 for a certain metal forming operation. You have to derive the final through strain and the flow stress that the metal experiences at that strain, and the average flow stress is 493. So when plastic deformation is there, when the material is deformed plastically, that the deformation or the strain becomes non-linear, and then you have the average flow stress given by the formula at k epsilon to the power n by 1 plus n, where Your K is your strength coefficient, okay, and N is your strain hardening exponent. So here in this question, exponent was given as 0.25 to you, and strength coefficient was 680 megapascals. Okay, so average flow stress was also given as 490. So you just have to plug in those values in the particular equation of average flow stress, and you can easily find out the flow stress that is asked in the question. Okay, so the sixth question was to find the yield, to find what yield criteria explained dash flow will take place when the stress exceeds your critical value. So first blank is common for all. Then you have plastic and elastic. Of course, all this yielding happens after the beyond the elastic point. So that second blank goes to plastic. And then it is a Tresca's criteria. So maximum shear stress comes into the picture. Okay, if it was bond mesures, you would have the principal stresses in the picture. Okay, so now in a rolling process, the two rolls rotate in what direction? So you know, the if both were rotating in the same direction, then the drawing of the product where between or sheet between the two rolls won't be possible. So the two rolls must be rotating in opposite directions so that the sheet can be rolled in between the two. So option A is the correct option here. And then you have the eighth question is asked, which of the following is not a type of extrusion process? So in that case, direct extrusion, hydrostatic extrusion. So stepping extrusion process is not a type of extrusion process. And so this one becomes your correct option. Okay. So the second and last question was deformations of solid are observed at what point? So there are two basic partitions of any stress strain curve, that after the elastic point, the plastic deformation begins. So in that case, up to after the elastic point, the material starts yielding, and and from that point, the material deforms plastically, and they can't revert back to the original dimensions, right? So in that case, elastic deformations of the solid are observed before the yield point, right? After the yield point, the material starts deforming plastically. And the last question is a simple formula. When a material tensile specimen is stretched from length L1 to L2, then the true strain is given by natural log of your final deformation to your initial deformation, okay, given by negative sign. So yeah, so I hope all these questions are clear to you. If so, we will start bringing out some of the concepts of this week's content and some corresponding problems related to that. Okay, so let's start. Pardon the background noise if you are having. There is a fest going on at IT Kanpur actually, and it is not possible to know that. So let's start with some of the concepts and corresponding problems out of your week 8 content. Okay, so regarding that, so I guess you guys have gone through the lectures of this current week, and if it is so, then you must be knowing about your Strukowski's method for single crystal growth of silicon, right? In that case, this is a question out of that. It says that during a single crystal growth process of silicon with a temperature of it's actually an ambient temperature, which is your 25 degrees centigrade. You are having a convective heating inside the crucible at a temperature of 1400 degrees centigrade. Now, you have to find out the cool rate of seed through a fusion zone of 100 centimeter thickness. If your heat conductivity of silicon is 2.3 watt per centimeter Kelvin, and the latent heat of fusion is your 1787 kilojoule per kg. Okay. You can take the density of silicon as 2.33 gram per centimeter cube. All right. So give it a try. We'll discuss it in a short while. Okay. So you must be knowing a relation between your cool rate and thermal gradients during this single crystal of silicon formation loop thread process. Yeah, so you can use that. It's a simple equation. So using that and plugging in all the values together, you can find out your flow rate. Okay, so give it a try. Okay, so let us discuss those questions and question in detail. So, uh, so let us first discuss what actually this single crystal growth process is. Okay, if you don't remember, recall. So in that case, you know that the Socrates growth method consists of a chamber in which inert conditions are maintained, and in that case, chamber in which your inert conditions are maintained, and then there is a melt, a silicon melt, which is there inside the chamber, and you take up a seed which you rotate, it sit inside the melt, and then pull it up while rotating inside that, so that the molten material gets clean to its surface when moving upwards and gets solidified gradually. Now what happens is, because the melt is there inside the chamber, and while pulling it, some extra material gets cleaned onto your seed, and with solidification on exposure to ambient, some extra material solidifies, okay, which then needs to be removed again through any wet sewing process or something like that, so that you pull out your pure crystal. Okay. Now in this question, they say that uh, your ambient has been 25 degrees centigrade, okay? And your the temperature at which the silicon is melt is 1400 degrees. Now you have to find out the cool rate. Okay. Now, if you remember the formulations during Zolkowski's method, what you have is uh, so what you have. So what you have is a fusion zone. Okay. You have a fusion zone. Okay. Through which your seed is being pulled out. Okay. If Q is the heat transfer rate of the seed towards the crystal side, and the Q1 of X be the heat transfer rate towards the melt side. Okay. Where this is happening at temperature T1 and this is happening at temperature T2. All right. T1 being greater than T2, of course, it is the liquid side and this is solidified metal side. Now, you just do the heat balance, then by using Fourier's law of heat conduction, you have on one side you have your conductivity, thermal conductivity of the liquid multiplied by the area and the thermal gradient. Okay, this happens to be at your this side, the entry side. Okay, this side B1, side B2. So this being at 1 being equal to your solidified materials conductivity area, and then your thermal gradient, okay, at the other side. plus so this is this side and this is the other side. Now if you do the heat balance, then what happens is total heat transfer rate at the liquid metal side to that at the subtracted from that on the other side, that is the crystal side, get your latent heat, okay, multiplied by your rate, which is GST, okay. Now then what you do is, sorry, this is a DMDT actually. Okay, so rate of mass transfer M and L. Okay, now this is the total heat rate due to conversion from liquid to solid. Okay, now when this becomes maximum, this becomes maximum when the heat transfer at the uh, when your heat transfer at the liquid side becomes zero, isn't it? So if you want to rearrange this equation, what does it become? So this becomes your L dmdt being equal to your heat transfer rate at the solid side minus of that solid side minus of heat transfer rate at your liquid side. So when does this LDMDT becomes maximum? Okay, this becomes maximum, of course, when the RHS of system becomes zero, isn't it? So considering that, what you have is maximum, your maximum V. Okay, so you can write it as you can change the mass transfer rate into you can break down the mass as your rho and velocity, okay, so and multiplied by your area, is equal to rho v. So from that you can do your rho multiplied as your no, L and area, okay, and then your dxdt, which is your velocity, you can say, being equal to, this is zero, you have this as ks into a into dt dx on the solid side. So using that expression, you can find out your dx dt or vmax, okay, as K A by L into GTM. Okay, or you can also write your rate of metal pull out DMDT as K by rho L. So you can take that out of this equation. Fine. So I can write DMDT equal to K by rho L into dt dx at S. Now let's revert back to what your question says. So in your question, okay, it was asked, so in the question, so let us pick it up. Okay. It is given that what is your dt, okay, that is your melt temperature minus your ambient temperature. Okay, so this is the melt and this is the ambient temperature. So this happens to be your 1400 minus your ambient temperature 25. Okay, so that is gives you approximately 1375 degrees centigrade. Okay, what is your dx? That is your fusion length of your fusion zone, which was given as 100 and 100 centimeters. If you convert that to meter, then it becomes your 1 meter. Now, conductivity of silicon was given as 2.3 watt per centimeter Kelvin. Okay, if you convert this to meter Kelvin, okay, so this becomes 2.3 into 10 to the power 2 watt per meter Kelvin. Okay. So next is your latent rate of fusion L, which was given as 1787 kilojoule per kg. So what does that become? 1787 10 to the power 3 Joule per kg. Okay. So what else do we need? We have got dt, we have got dx, we have got k, we have got l, we have also we need rho, right? So rho is given as your 2.33 gram per centimeter cube. So this turns out to be almost 230 per meter. Now you plug in all these values to your principal equation. This is your pool rate, okay, dmdt. This is a thermal gradient. This is conductivity divided by density into latent heat of fusion. So when you put that all these things here, you get dmdt being equal to k by rho l. K is your 2.3 into 100. That becomes 230. Okay, watt per meter Kelvin. 230 watt per meter Kelvin divided by rho l. Rho is your 2330. And your latent heat of fusion is 1787 into 10 to the power 3. Okay, what else is left? dt dx. Your dt is 1375 degrees centigrade. Okay, so you convert it to Kelvin, and that becomes your 1375 plus 273, which is 1648 Kelvin. Okay, so multiplied by 1648 divided by what else is left? So 1648 divided by your length of fusion zone dx, that was 1 meter. Okay, so just you do that calculation and find out how much it becomes. So it almost becomes 379040 divided by 330 1787 is almost equal to 4163 710. Okay, so when you divide that 379040 divided by 41637, so that is almost equal to your 9.1 to 10 power minus 5. Okay, so this is your rate of pull out, that is in kg per second. Fine. So this is your final answer. Hope everybody got this. If not, you can please ask your doubts. Okay. Okay, so let's start with our next problem. Uh, so if we go to our next problem, so your next problem is a question out of your etching, concept of etch selectivity, which you all have done, I guess. In that case, that a substrate damage is more when etch selectivity is 1. Okay, so you know that how do you define your etch selectivity? Yeah. So etch selectivity is something which defines how much area of your when you do the etching, how much area is over etched. Okay, to what is your actual requirement of etching? Okay, now selectivity is defined as your etch rate of the bottom layer. Okay, of your substrate, you can say, to the etch rate of your mask layer of the vertical walls. Okay, so in the right hand figure of the display screen, you can see that your top arrow, where the top arrow is being shown, you can see the etching is more. In the other case, the etching is less. The bottom surface, okay, or the substrate surface. So the top one is your lower etch selectivity, and the bottom one stands for your high etch selectivity. So of course, high etch selectivity is always preferred during etching of silicon because your bottom layer is more maintained in that case, and in case of low selectivity, your bottom layer is more eroded. So in this question, your first option becomes your correct option. Okay. So do you have any doubt with that? So if not, then we'll move to our next topic, next question, probably, which is something related to etching again. Now the question says a microchannel is etched in a 100 planar wafer with QH solution. Now in that case, you have to determine the angle between the channel wall and the front surface. If the top channel, secondly, the top channel and the edge greater 100 microns and 1 micron per minute respectively, then what is your bottom channel width after 20 minutes of etching? Okay. And how long will it take until the etching process stops? So give it a try, and then we'll discuss the question in detail. So let's discuss the problem with you. So let's discuss the problem with you then. Firstly, it is saying, it is asking to determine your angle between the channel wall and the front surface. Okay. So your channel wall. Okay. So that is if we check the diagram. Okay. The angle between here the etching is happening in 100 direction, as it is already told in your question. So the channel the angle between the channel wall and the front surface becomes the angle between your AB and your BC. Okay, the angle alpha. Okay, So how can you find the angle alpha? It is like if you look at the diagram, you can see that AB is perpendicular to your DE line, isn't it? Also, it is perpendicular to your AC line, isn't it? Now, suppose because the perpendiculars, then if your uh, AB line, okay, uh, your AB is 2 by 2, okay, and then so if your AB is 2 by 2, and then the height AB is 2 by 2, okay, and then the angle alpha you have to find out. That becomes your because AB and AC, these are perpendicular to each other, isn't it? See the symbol. In that case, tan inverse of AC by AB gives you the angle alpha in that case. Right? Now, this is given as your 1, you can see from the diagram, and your AB is root 2 by 2. So that the angle becomes 1 by root 2 by 2. Arc, I mean tan inverse of that gives you 54.74 degree. Okay. Now, what I mean to tell you is, so suppose here, as for the diagram which is given to you. Okay. Suppose this is your line DE, okay, and this is your AB. This is the 0, 1, 0 plane. Okay. This is your 0, 0 plane, which your this thing etching is happening, and then so here you can see A and B. So you see these are all unit length. This being your E. These are your 100 planes again. Now this angle you have to find out. Okay. This angle your AB. So you can see from the geometry that your AB is your root 2 by 2 units, okay, and then AC, yeah, AC is your 1 unit, isn't it? So what is the angle alpha between AB and AC? AB and AC then? Because AB is perpendicular to AC, you can say that alpha is your tan inverse of AC by AB. Okay, so that becomes your tan inverse of 1 by 2 by 2. How much does that become? 54.74 degrees. Okay. So this answers your first question. So this answers probably your first question. The second question says, The top channel and the H rate 100 microns and 1 micron per minute. Then what is the bottom channel width after 20 minutes of etching? Okay. So let's switch back to our writing pad. Let's switch back to our writing pad. Your question says that top channel length of your top channel is 100 microns and the H rate is 1 microns per minute. Okay. You have to find out after 20 minutes of etching what happens to be the bottom channel. If you look at the diagram, it is like this is your bottom channel, and suppose it meets at any arbitrary point O. This is your top channel width. It's given as your 100 microns. Yeah. Let's take this particular distance as D. Okay. Question is asked that what happens to your bottom channel? Okay. This thing after 20 minutes of etching. Okay. These are your one-on-one planes, and etching is happening along the 100 planes. Okay. So in that case, when the top channel width is this and your H rate is this, what happens to be the channel depth after 20 minutes of etching? The H rate is this, so you know distance is given by your speed 1 microns per minute into your time is 20 minutes. Okay. So this becomes 20 microns. Now we move to what is the previous diagram. You can see project up channel down. Okay. So if you subtract if this part be y and y, if you subtract twice of y from the top channel length, which is the whole thing, this one, then we'll get the bottom channel length, isn't it? So you can get concept, your bottom channel length becomes as bottom equal to L top minus twice of y. So what is your L top? That is 100. And what is your y then? So we have found D is 20 microns. So how much does your y then become is okay, D by tan of alpha, alpha being the angle between your 100 and 111 planes. Okay, this being alpha, so this also becomes alpha. So you do twice of D by tan of alpha. So you have already found out your D is 20 microns, alpha being 54.74. We have found out in our first question. So what does L bottom then becomes? Almost equal to 71.7 microns. Okay. So this concludes your second question also. I hope you got it. So we'll move to your third question, which is what? How long will it take until the etching process stops? Okay. So when will the etching process stop? So actually, this is your top channel length and this is the bottom channel length. Right? So etching process stops when the two 1-1 planes meet, isn't it? This is 1-1 plane, 1 plane. When this meet, the etching process will stop, of course. So, and what have we found out is your total width, okay, of your bottom channel. This is bottom channel, right? So when the width of your bottom channel, or you can say the length of your bottom channel, because we have used length earlier, so length of your bottom channel becomes 0. That is the condition when H stops. Okay. So earlier you have used this equation. From that you can see that your okay. So length of your top channel minus twice of okay G by alpha. When this is alpha, okay, this length is D 0. Or you can say by n alpha be your NOD. So from that, alpha. From that you can find Dmax, that is the depth at which the etching stops. Okay, so Dmax being your 110 alpha by 2, which becomes your 110 of 54.74 by 2, which is nothing but 70.71 microns. Okay. Now your question is time at which your etching stops. How do you find time? You know the distance, okay, you know the speed as 1 microns per minute. So your time becomes a distance divided by speed. That is a Tmax divided by speed or H rate, which is given as 1 microns per minute. Okay, so that becomes so 70.71 divided by 1 in minutes. Of course, microns get cut off. Okay, so that gives your 70.71 minutes. Okay, so that is your sorry guys, I just got logged out due to some technical error. So this was where we were last minute. Okay, so we have found out your time at which the etching stops, where Tmax being the total depth up to which the etching happens after 20 minutes of etching. Okay, and this is the maximum depth to which you can etch. Okay, and this is your etch rate. So when I divide this, I get your time at which the etching stops. Okay. So I hope this problem is clear to you. If it is clear, then we'll proceed to our next problem. You can please ask doubts if you have any regarding this topic. Okay. Okay, guys. So if it is done, then let's discuss some thing about your photolithography process. You know, one of the mostly popular your microfabrication technique is the photolithography process. So probably you're aware of the basics of photolithography. To start with, actually, photolithography is an uh, very widely used for fabricating microstructures. Okay, and some substrates are mainly used as silicons, glass, etc. And then depending upon your type of the energy beam from which the process is happening, the lithography gets to be divided to photolithography, electron beam lithography, X-ray lithography, okay, and lithography, etc. Now, patterning process, photolithography is limited to your 2D structures. Okay, you can't make 3D structures actually. Now, this technique uses a photosensitive emulsion layer called resist. Okay, now resist can again be of two types. Okay, if you are directly making your resist through directly making if you're directly making same patterns, if you want to make the same patterns as your mask, then we use a positive, we use a negative resist. Okay, and in the other case we use a positive resist. So resist can be of two types, maybe positive or negative. Okay, now basically there are three major steps, happens to be three major steps of photolithography. so first one happens to be your positioning process. Okay. Second one happens to be your, talking about photolithography. Second one happens to be your exposure process. Okay. And third step happens to be your developing process. What are these three processes basically? So positioning is your mask through which you are going to expose your resist coated substrate. Okay, so these are to be aligned, isn't it? To before the exposure process. So this is your positioning process. Then you have to adjust the distance between your mask and your substrate. Okay, so that has to be an optimal distance between your mask and substrate. Between your mask and your substrate. And then because otherwise there can be diffraction of the beam happening, accuracy and perfection of the microstructures. In the other case, there can be gluing action between your resist layer and your mask. Then that would mean reduction in repeatability of the process. Okay, and then you have your exposure process in which your resist layer is being exposed to an optical or X-ray exposure scheme. Okay. For which through which you transfer the patterns to your resist layer by changing the properties of the exposed areas. Fine. So lastly, you have a development process. Okay, you have a development process in which you dissolute or etch the resist pattern which has been debonded. Okay, so these are your major steps of your photolithography process. Okay, so this can be asked in your papers or your exams actually. So we should discuss it here. If you have any doubts or questions, any queries, you can ask me. Okay. So to explain you, actually, we are talking of photoresist types, right? They can be a positive photoresist, they can be negative photoresist. So how do we decide what type of resist we need to use? Okay, so we go to your positive tone photoresist on one side and negative tone photoresist on the other side. Okay, so suppose you have a silicon wafer here. Now what you do is we told the first step is your positioning. Okay, so before that you have to coat actually the resist layer to your substrate, isn't it? So there is a process called spin coating in which you drop cast your resist layer over your substrate. Okay, and then rotate it at a particular speed, which determines again your thickness of the coated layer. Okay, so this be your resist coating. Okay, and then this be your substrate. So now you what you do is you do the patterning. Okay, so actually to improve the bonding you can sometimes to coat a adhesion promoter layer before your before putting your register. Okay? So that actually improves the bonding of your register substrate. So this is nothing but an adhesion promoter. So once you have done that, you need to do the patterning. Okay. So if this be your substrate, this be your adhesion promoter layer, but that you have your spin coated layer. Okay. So now you do the patterning process. Okay. So suppose you expose some areas to the source. Okay. And then leave some other areas. Okay. So after this thing, you do same for both. So here also you have a substrate, you have a coating of adhesion bond, you have a coating of photoresist. Okay, again you have substrate, you have a adhesion promoter layer, you have a photoresist layer. About this to do the patterning. So what happens is when you have used a positive photoresist, any of the regions which have been exposed will wash away. Okay, so what remains is so if you project it out, anything which will be exposed will be washed away. Okay, so the exposed areas goes away and the unexposed areas remains. Okay. So this happens to be your last step, the developing step. Okay, which gives you this type of patterns in case of positive resist. Okay. In the other case, what happens is it's a negative. In case of a negative tone resist, okay, any of the areas which you expose to your UV or X-ray, what happens is any of the areas you expose remains and the unexposed areas washes away. Okay? So what I meant to tell you is these portions which are unexposed will wash away. Okay? And the areas which have been exposed will stay there. Okay? So yeah, so that happens to be your negative tone resistor. Okay. So these are the two types. I hope you got it now. So you need to have a clear idea because you can find some questions out of this. So next will, I hope it's clear, right? This clear will to the last topic of today's session, which explains you, it shows you the steps of photolithography process. Okay, so in detail. So majorly we have a positioning step, exposure step, and a developing step, right? But in detail, what you have to do is, firstly you have to do the substrate cleaning, isn't it? So you have to do your substrate cleaning. You have to really be careful in doing the cleaning because these are micro fabrication processes, and any small particle or settle down dust may cause a perfect surface. Okay, so you have to be really careful while doing substrate cleaning. Things like piranha solutions are used to do the cleaning process perfectly, and then once that is done, you go for spin coating. Spin coating is the process by which you can coat the substrate by a desired thickness of photoresist layer, which we have just explained here, right? So after spin coating, you do the pre-baking of the do the pre-baking of the resist layer, which makes the resist actually photosensitive. Okay, this you do before you expose it to the X-ray beam or optical source or whatever it is. But pre-baking is necessary to make it photosensitive. Okay, so pre-baking actually we go to the exposure, and after exposure we do the post-baking. Okay. So once post baking is done, we go and develop the solution, develop the resistor to remove the unbonded parts. Okay, so this happens as per your resistone used. Okay, so in case of positive tone, this type of removal will happen after developing. In case of negative tone, this type of removal will happen. So after developing, we again do your post hard bake. Okay, post bake. Now this happens to a hard bake. So of all these bakings, there are certain defined or standardized temperature and time scales which you have to maintain as per your requirement. Okay. After post bake, we go for your etching if it is required, of course. Maybe in case of glass, sometime you can do that. And then strip off the photoresist, which is again called your lift off process. Okay. This is actually called your lift off process. So this happens to be your complete. This happens to be your complete lithography process. You do the substrate cleaning, you do the spin coating, you do the pre-baking, you do the exposure, you do the post-baking, you develop the resins layer, you do the hard baking, okay, you do the etching if needed, and then you do the lift-up process to get your final product, okay, final features of the surface. Okay, so yeah, so this pretty much concludes today's session. Sorry about the glitches we had during today's session. There are a little disturbances around. So you can go for any queries or doubts if you have. still have around 10 to 15 minutes before we conclude. So please go for the Q&As. Thanks. Okay, guys. So let's close today's session, and we'll meet in the next session. Okay. So good night.